All right, hello, this is Mr. Fawcett, and the lesson today is going to be on properties of limits. So basically, there's a bunch of different properties of how you can manipulate limits to make them easier for you to evaluate, and we're going to talk through most of them today and then give you a chance to practice applying those properties. Okay, so let's start with our little intro activity. We are given two functions, f of x and g of x, and we're given a bunch of limit expressions for us to evaluate. Now, we're not going to use the limit properties that we're going to talk about later in the lesson, but we're going to perform the operations on the functions first and then take the limit of the resulting function. So I'm going to, actually, one second. All right, I just had to pull up my whiteboard feature. So we're going to go through, I guess we'll go through one or two of these, and then we'll jump to the actual limit properties. So let's start with number one. The limit as x approaches 4 of the quantity f of x plus g of x. So we're going to add these two functions together, and then we are going to take the limit of the resulting function. So in my brackets, I'm going to have x plus x squared plus 7x. And we're going to take the limit of this function. Now, again, this function is continuous at x equals 4, so we can apply direct substitution. You could simplify what's inside here first. It doesn't matter, though. It's going to give you the same answer. So when I apply direct substitution, I'm going to get 4 plus 16 plus 28, and that is going to give me 48. Okay, and of course, I encourage you to double check the math on your own. Let's jump down and do number 4, actually. So need to remember what those functions are, x and x squared plus 7x. And let's do some multiplication. So I'm going to have the limit as x approaches 4, and then in my brackets I'm going to have x times the quantity x squared plus 7x. Okay, so I'm going to have to do a little distributing. I'm going to get x cubed plus 7x squared. Again, this function right here is going to be continuous at x equals 4, so we can just apply some direct substitution. 4 cubed is going to be 64. 4 squared is 16 times 7, which is 112, I believe, which is going to give us 176. So these weren't too bad because the functions were not too complicated to work with. Now, if I had given you, more complicated functions, performing these operations on the functions may be pretty difficult, and you may want to actually evaluate some limits first before you perform the operations on the function. So let's go to the next page and talk about some of these limit properties and how they may help us out. So before we actually talk about the specific limit properties, we're going to look at a scenario that kind of leads from the conversation I was just having. The limits above were not likely that difficult to evaluate since I chose functions that work nicely together. However, let's look at the example below. Is there an easier way to evaluate the given limit than dividing the functions and then evaluating the limit? So take a look at the limit, see what you think about the process of dividing those functions and then taking the limit. See if that seems doable. If not, think about what other thing you could try or what other ideas you may have about how to evaluate this limit. Okay, so maybe you've attempted this several ways. If you were to divide these functions, well, it's not really clear what you would do, right? Because there's no cosine factor in the numerator, and we can't divide 4x cubed by cosine of x. So that's not really going to work, right? And hopefully there's another way to do it. I'm guessing most of you thought that you could substitute in 0 to the numerator and substitute in 0 to the denominator separately and then divide the functions. And that makes sense. We've kind of already done that when we've talked about indeterminate form. We've talked about evaluating the limit of the numerator and then the limit of the denominator. I just didn't explicitly talk about that limit principle because I thought the other content at the time was more important. But we are allowed to do that. We are allowed to split it up and take these two limits separately. So we could just say find limit of numerator and denominator separately, and then divide. And we're not going to go through this one specifically, but we are going to have plenty of time to practice later in the lesson. The next page does have those limit properties that we're going to walk through, and then you're going to have some time to apply. Okay, let's jump to that next page. So properties of limits. Suppose that the limit of f of x as x approaches a equals L, and the limit of g of x as x approaches a is equal to m. And L and m are also going to be real numbers here. So if we look at number 1, and we are adding two functions together and taking the resulting function's limit, well, we can take the limit of each function separately and then add those together. Okay, and this would just be equal to L plus m, right? If the limit of f of x as x approaches a is L and the other one is m, then we would just be adding those together. Same thing for subtracting. It's the same idea, obviously. And again, you can pause the video if you need more time to copy these down. Let's do division. So this is the example we just talked about. This should be x is approaching a, not a is approaching a. Oops. So we'd get L divided by M. All right, I'm going to scroll down to the next couple. I guess I can fit them all in on this page, or in this screen. Again, if I am multiplying them together, I can just find the limits of each separately and then find the product. You guys probably have more space in your boxes than I do in mine. Okay, number 5 is a little different. C is a constant. So they're saying multiply a function by a constant and then find the limit. Well, I can just pull the constant outside, right? So I can have C times the limit as x approaches a of f of x, and then I get C times L. So I can just apply the constant at the end of the process rather than applying it first. Number 6 is where we have a function raised to a power. So instead of raising the function to a power first, right, I can find the limit of the function first and then raise that limit to a certain power. And this is going to give us L to the power of P. And finally, for number 7, we have the limit of a constant function as x approaches a. So I think this one is much easier done with a visual. If I have my axes, and I have my constant function, we'll just say that's 3. Oops, I know it's going to do that. We'll say it's 3. You know, it doesn't matter what x approaches on this constant function. My y value is always going to be the same, right? So it doesn't matter what a is, right? My answer is going to be c, right? Because my c is really 3. C equals 3. Okay. Again, if you need to think through these, you can just pause the video before you move on, but we are going to do some practice. I'm going to do a couple examples using graphs, and then I'm going to do a couple examples. I believe we have some tables down. No, we don't. We have some algebraic functions down here. I'm going to go for about 5 or 6 minutes to try to keep this video a little bit shorter than the other ones. Then you can try the others on your own. All right, f of x on the left, g of x on the right. So the first one we have the limit of, as x approaches 2, this is a one-sided limit because we're approaching from the left-hand side, the negative side, of f of x plus g of x. So the first thing we're going to do is break this apart. Right, so we're going to evaluate the limit as x approaches 2 from the negative side of f of x plus the limit as x approaches 2 from the negative side of g of x. So we just split this limit up here into 2 different limits using our limit properties. If I go over to my f of x graph, as I approach 2 from the left-hand side or the negative side, I'm approaching a y value of 3. And if I approach 2 from the left-hand side on my g of x graph, I'm approaching a y value of 1. So 3 plus 1, that gives me 4. And that would be the answer to this limit. All right, let's do one more on this top row so that I can still keep the graphs on the same page. Okay, we're going to do number 3. Same idea here. We're subtracting. And we're finding the actual limit, not a one-sided limit. As we look at f of x as it approaches negative 3, this limit does exist, even though the function does not exist at this point. We're approaching negative 2, which is okay, minus g of x as x approaches negative 3. And here we start to run into a problem, right? Because we're approaching negative infinity and we're approaching positive infinity from the other side. So even if they were approaching the same infinity, we would say that the limit does not exist because they're not approaching real, the one-sided limits are not approaching real numbers. So if one of these limits does not exist, right, we can't add something that doesn't exist to negative 2. Does not exist is not the same thing as 0. We actually just don't have an answer here. So our final answer, if one of these does not exist, then our overall answer does not exist. All right, that's enough for the graphs. Let's look at, of course you have the other ones that you can attempt, but we're going to do 1 or 2 algebraic ones. Okay, let's do a division one. That's good. And then I think we'll do C, a square root one. So if we look at A, we are going to do the limit as x approaches 3 of 5. Well, actually, there's 2 steps we're going to do here. And I'm going to do them both in one swoop. So I'm going to pull the 5 out, because there's 2 limit properties here. So it'll be 5 times the limit of f of x as x approaches 3, divided by the limit as x approaches 3 of g of x. Okay, so the limit as x approaches 3 of f of x is 2. So we have 5 times 2. And the limit as g of x approaches 3 is negative 4. And again, I'm just finding these right up here. They're given. So this gives us 10 over negative 4, which is equal to negative 5 halves. Okay, and the final one we're going to look at is part C. So it may be easier to write this radical as an exponent because our properties were in terms of that one property dealing with exponents. We didn't have a radical property. It was in terms of the exponents or the power property. So we're going to rewrite it. So this can really be rewritten as the limit as x approaches 3 of 4 times f of x raised to the power of 1/2, because the square root is equal to the power of 1/2. So there's a couple different things we need to do here. We can actually apply the power rule first. I'm going to apply it to 4 and f of x. So I get the limit as x approaches 3. 4 to the 1/2 power is 2 times f of x to the 1/2 power. Okay, now I'm going to rewrite it up here. Oops. So I'm going to bring the 2 outside. So 2 times the limit as x approaches 3 of f of x. And that entire limit portion is going to be raised to the 1/2 power. Again, if you're unsure of the algebra there, just think through it step by step. I get 2. The limit of f of x as x approaches 3 is 2. I should have some equal signs here. So I get 2 times the square root of 2. Again, I think that last one was the toughest. It had the most steps, but they were, once you apply the limit properties, they're just algebraic steps. Okay, I'd encourage you to attempt the rest of these in the packet. As always, write down any questions and come prepared to ask them the next opportunity you have. All right, this is Mr. Fawcett. Enjoy the rest of your day.